Hey there, random video watcher. I hope this uh, video finds you well. What we're going to be taking a look at in this video, in this lesson, is going to be how to integrate transcendental functions. A lot of the things that we're going to be looking at in this lesson are going to focus on things like exponential functions, log functions, and inverse trig functions. I don't think that we're going to really see much in the way of integrating a straight trig function, even though if we're not going to see them much in this material, you may still want to have this handy as you're working out any problems associated with integrating functions that are transcendental, in this case the trig material. Uh, Also, if you don't have them memorized, you may want to just go back and refresh yourself on what the derivatives of inverse trig functions are going to be. Most of what we're going to be looking at for the material in this presentation really is going to be kind of these things here. Like I said, we have exponentials, we have log stuff, and we're going to have maybe something to a power. There are going to be some inverse trig functions that we're going to be taking a look at, and these take some time to really kind of familiarize yourself with them. They don't always just kind of jump out at you. The thing that you want to take a look at with the inverse trig stuff, if you are trying to integrate them, is really you want to focus on what you have in the denominator. To see, do you have something that is squared, like underneath the square root, like you see for arcsine and arcsecant, or do you have something that is just the sum of two squares, like you see for arctan? Now we're going to see a couple of examples where it may not be given to you directly that that's the case, but you can actually create something like that using some other algebraic principles, specifically how you complete the square of a quadratic. So here we are going to be using U substitution in a lot of these examples in order to make things a little bit simpler to understand. So let's go ahead and get started here. Let me make sure my pen's not going to be too wide. Okay, so we are going to look at using U substitution for a lot of these problems, and as we've seen in other integration techniques or even derivative techniques when it comes to logarithms, it's going to be beneficial to rewrite the logarithm. I don't feel like necessarily breaking it up completely, but we can look at it as the indefinite integral of 1 over 3x natural log of x, using that property, the power property of the logarithms, dx. We're just taking that exponent of 3 and moving it into the front of the logarithm. So this is where we're going to start doing our U substitution. Identify something that if you can take the derivative of it, you will find it somewhere else in the problem. Now this one doesn't stand out to you right away as far as like if I take the derivative of something, am I going to find that somewhere else in the integral? But in this case, we want to look at just the natural log of x. Because if I do take the derivative of that, du, we're going to wind up with 1 over x. And you can kind of see where the 1 over x is. And I forgot to write, hold on, let me add my dx here. Dx, forgot to add my dx. And you can kind of see right here, we have the 1 over x dx. But if you notice, we do have that 1/3 also. So we can pull that out as a constant when we before we perform our integration here. So now that we have our u value identified, here we can kind of rewrite the integral to be the indefinite integral of, and in this case, we'll go ahead and pull out the 1/3. And so that will give me uh, 1 over u du, or du over u if you prefer to write it that way. Well, we can go ahead and take the integration at this point. So the integration of u, I'm sorry, 1 over u will be 1/3 times the natural log of u. Well, natural log of u, I don't want to, plus a constant of integration. And now we can take the expression that we had for u and just drop it right back in there. And I wind up with 1/3 natural log of x plus a constant of integration. And that is how we're going to take a look at incorporating u substitution with some transcendental expressions, functions in this case, of using natural log. So let's move on to example B and just see how we're doing here. This one, there's really not much in the way of anything that I want to rewrite necessarily, like I did in the first example. But again, look for something in the problem that if you take the derivative of it, you will find it somewhere else in the integrand. And a lot of times when we have the ratios that are like this, it's a good idea to start looking at the denominator to think of that as u. And you can think, well, obviously sine and cosine are going to be derivatives of each other, so it doesn't really make a lot of sense to necessarily pick one, to think of just one or just the other. But specifically, I'm going to, for this problem, look at what is in the denominator, and that's generally what I would do whenever I have a ratio for my integrand like that. That's not 100% of the time like a lot of other things in mathematics, but here I'm going to look at u to be the denominator of 2 minus, oops, I forgot the 3, 2 minus 3 cosine of theta, 3 cosine theta. And again, I want to take the derivative of that. So the derivative of this, in this case, will be a positive 3 sine of theta d theta. And so if we look at the values that we have here, there's our sine of theta d theta, but it doesn't quite match what I have here. So I do need to take the 3 on the right side of that equal sign and move it over by multiplying both sides by 1/3. So this will give me 1/3 du to be equal to sine of theta d theta. Now it matches, and we're going to have this constant. We'll have this constant that'll be in front of our integral symbol when we perform our u substitution. So let's see what we end up with here. Okay, let's pick a color. So now I'm going to say, in this case, I have the constant 1/3 times the indefinite integral of, in this case, again, you can say 1 over u times du, or du over u, whichever you prefer, and start taking the integral. And this one looks very similar to the previous problem where we had the 1 over u. So I'm going to have 1/3 times the natural log of u plus a constant of integration. And in this case, we substitute the u value that we had again, and I'm going to wind up with 1/3 times the natural log of, what did we have? 2 minus 3 cosine of theta plus your constant of integration. And of course, we want to make sure we take the absolute value of that, because remember, the domain of a logarithm has to be greater than 0. So that's why we take the absolute value of it, and there we go. That is the first couple of examples that we're looking at to see how we're going to try working out these problems using u substitution in transcendental functions. So here on this example, or on these two examples, I want you to go ahead and pause the video and try working these problems out, and then hit play and check your work with mine, and just to see how well you're picking up with it. Uh, so go ahead and pause it, work it out, hit play when you're done. So how did you do, my intrepid calculus student? Looking at the first one, again, sine and cosine are kind of derivatives of each other, but so I'm going to kind of want to look at the bottom for my u expression. So I'm saying u is equal to 1 plus sine of t, and the derivative of that, cosine of t dt, which matches what the original integrand would have been. So the u substitution will give me the integration of 1 over u du, or du over u, however you prefer it. The integration of the u expression will be natural log of u plus a constant of integration, and at that point we can substitute the expression 1 plus sine of t back in for the u value. Looking at the next one, here we're looking at something e raised to a power, so I'm looking at the expression of the exponent of e. Because I have something x cubed, if I take the derivative of that, I will wind up with the x squared term that's in the integrand. So I'm looking at 1/2 x cubed as my u value, taking the derivative there will give me 3 over 2 x squared dx. But of course, the 3 over 2 is not present in the original integrand. So multiplying by the reciprocal gives me 2/3 du to be equal to x dx, and now we see the x dx kind of matches what the original integrand is. So we'll have the constant 2/3 in front of the integral symbol, and I wind up with 2/3 with the indefinite integral of e to the u du, and the integration of e to the u, just like the derivative of e to the whatever power, is just itself. So the integration of e to the u is just e to the u power. So I wind up with 2/3 e to the u plus c, and then substitute the u value back in, and we wind up with 2/3 times e to the 1/2 power, or e to the x cubed over 2 power plus c. So moving on to the next examples here. In this case, I want to go ahead and work these out simply because I know some kids are going to get thrown off with the cotangent expression, and on F we're working with a power function that we need to take a look at. And so let's go ahead and start working on E here and see what we end up with. So in the last couple of examples, what I did whenever I had a trig thing is I kind of looked at the denominator. Okay, but in this case, I really want to pay attention to what the exponent is here, because I can rework cotangent in some way to get to a sign using derivatives. So I'm going to go ahead and look at u in this case to be cotangent of x. And again, you may need to go back and review your trig derivatives if you need to. So here in this case, du, the derivative of cotangent of x, is going to be negative cosecant squared of x. So negative cosecant squared of x dx. And as you can see right now, negative cosecant isn't present in the original integrand. So this is where we want to, utilize that relationship that we understand. Well, cosecant is going to be the reciprocal of sine. So I can pull out the negative that's on the cosecant and make this negative du to be equal to 1 over sine squared of x dx. And now we can kind of see that, especially if we broke up the original integrand as being 1 over sine squared times e to the cotangent of x dx. Now we can kind of see where that this and this match. So now I do have that constant that goes in front of the integration, and in this case a constant of -1. So let's go ahead and start doing that. So I'm going to say negative indefinite integral. In this case, we're going to wind up with, where am I at? E to the u. That's going to be this part here. That'll be e to the u and du. And so the du, and I probably should underline the dx here. So all of the stuff underlined in yellow, that's du, and the stuff underlined in the blue color is e to the u power. And now we can start taking the antiderivative here. So again, the antiderivative of e to the u in this case is just going to be negative e to the u power plus a constant of integration. And now we can substitute, and I'm going to wind up with negative e to the cotangent of x power plus my constant of integration. And there is our final integrated answer. So moving on to the next one here. In this case, I really want to look at the exponent value here, because if I take the derivative of sine, I'm clearly going to get cosine. So let's take a look at that one. I'm going to say u is equal to sine of x. So du will be cosine of x dx. And now you can clearly see again cosine of x dx, cosine of x dx. So there's our du expression. So at this point here, we can go ahead and there's no constant that we need to work into the in front of the integral. So in this case, we're going to have the definite integral of 2 to the u power du. Now this is where you may want to, if you're following along with the notes, or just go back to the beginning of the video and then jump back here. This is where we're looking at an exponential rule here, where it's not e anymore. Okay, so with e, when I take the antiderivative of 2 to the u power, that's going to give me, we're looking at a to the u over the natural log of the a value. That's the rule that we're looking at from the beginning of the lesson for the integration of this exponential expression. There we go, if I can spit the words out of my mouth. So here I'm going to get 2 to the u power over the natural log of 2 plus a constant of integration, and now we can plug in the c value again, I'm sorry, the a value again, no, the u value, one of these days I'll get it right, and we'll wind up with 2 to the sine of x power, plus, over, let's clean it up a little bit, make it look like I actually wrote it correctly the first time, times natural log of 2 over natural log of 2 plus a constant of integration. And that is going to wrap up that one for example F. Now, G and H, again, this is one, these are two examples that I don't necessarily want you to try and work on your own unless you feel completely confident, because G especially, in my opinion, is trying to trick you, okay? If you go back again to the beginning of the lesson and you look at the table of, or you look at the rules that were given to you there, here on this one, we're going to be looking at this bit here. This is going to be what's going to throw people off, because a lot of people are going to want to look at that and just say, oh, that's you, and then they're going to want to try and do our u substitution the way we've done on the last several examples. But in this case, if you look at the rule for inverse tangent, or arctan, okay? The rule for inverse tangent will give you the definite integral, or indefinite integral du over, and in this case it says a squared plus u squared, nope, don't have anything here. But what that's telling you is that here we're going to have the rule, the derivative of this will be 1 over a times arctan, or inverse tangent, of, what was it, u over a plus a constant of integration. Let's see if we can move this guy out of the way a little bit. And a lot of people are not going to look at this denominator, this denominator. A lot of people aren't going to look at that and immediately recognize that it fits this pattern here to understand that we're doing inverse tangent. And that's really why I wanted to work this one out for you, as opposed to having you guys try to just, okay, here you go, good luck. Let me know what you get. Okay, so in this case, because we're using, because we're using this for arctan, in this case we're going to say, well, let me get a different color here. Here, u squared is going to be the 4x squared. So that means u would be equal to 2x, and du would be equal to just 2 dx, which doesn't match what we have in the original integrand. In the original integrand, we just basically have the dx. So that would give me 1/2 du to be equal to dx. So we do wind up with a constant that needs to go in front of our integral. Okay? So let's keep going. What is the a value? Because we still have an a squared value that we're looking at. So a squared in this case would be the 5. So a in this case would be the square root of 5. So the dx itself, we're not really going to be doing substitution back into the expression. I don't really, see the, if you want to, you can rewrite the integral here. You can say we have our constant of 1/2 times the indefinite integral of du over a squared, which was 5, plus the 4 squared, or 4x squared, which was the u squared. But we want to make sure that we can identify specifically what is the u value and what is the a value, because those are things that are used in the rule for the integration of arctan. So when I do that, oh, looks like it's time to go. I'm going to say 1/2 times inverse tangent of, nope, getting ahead of myself, 1/2 of 1 over a. So in this case, 1 over a would be 1 over the square root of 5. Now I'm going to say inverse tangent of u over a. So in this case, I have 2x over radical 5 plus my constant of integration. And we'll clean it up just a little bit. I'm not gonna bother trying to rationalize anything here. I'm gonna just clean it up a little bit and say that at the beginning we're gonna have 1 over 2 radical 5 inverse tan of 2x over radical 5 plus the constant. And that's what I'll call my final answer on that one. So like I said, that one's a little tricky because it doesn't just shout at you, hey, this is going to be inverse tangent, the way, like if you're looking at example H on the next problem, it very clearly is kind of shouting at you that we're using inverse sine in this case. So inverse sine in this case, the rule that they're giving us, going back to the beginning of the lesson, would be du over the square root of a squared minus u squared. U squared. And that would allow us to say, when I take the integration of it, will be inverse sine of the u value over u over a, plus the constant of integration. So what is what here? Okay, so in this case, we would say u, in this case, I'm going to look at u as being the inverse sine of x. So du is what, and again, this is where you might want to just go back and review your, trig derivatives if you're not remembering how to do the derivative of inverse trig functions here. This is going to be 1 over the square root of 1 minus x squared dx. So that's how we're kind of getting the derivative. That's, again, what is in the original integrand that if I take the derivative of it is going to wind up still being in the original integrand. And so here we see 1 over the square root of 1 minus x squared dx, and that's exactly what we're seeing here. Okay, just, understand it. We could say that, break it up with a 1, or 1 over that times inverse sine. But now that I have that, now it's time to go ahead and start doing our integration. So essentially what we have here is we have u. We don't have any constants being added in front of the integrand. So I have u representing sine inverse of x times du, which is the 1 over the square root of 1 minus x squared for this particular function. And in this case, we really didn't need this. Doesn't look like we really needed that. So, well, sometimes it just works out to be a little bit simpler. I was just looking at this. Maybe this is what we needed to begin with because we had something with inverse tangent or inverse sine. But in this case, looks like just doing normal u substitution is going to work out well. So here I wind up, when I take the antiderivative of this, I'm going to wind up with natural log of u. No, not natural log. I'm thinking 1 over u. That will be 1/2 u squared plus a constant of integration. So in this case, 1/2 u squared is going to be 1/2 times sine inverse of x, and that is squared plus c. So there we go on that one. I hope the beginning of that one didn't throw you off a little bit, because I thought we were going to need this at the beginning, just looking at inverse sine given in the problem there, but turns out we really didn't need it, because I can just do u substitution. If I said u is sine of inverse x, or sine inverse of x, I wound up taking the derivative of that and getting the remaining part of the integral, or the integrand, I should say. So there we go. Worked out simpler than I thought it was going to be. Now what we're going to be taking a look at is moving on from indefinite integration into definite integration, where we have a defined interval from a to b. And we will, again, kind of look at this similarly to what we've done with u substitution, where we can identify a new lower and upper bound with the expression that we have for u, going from with our u substitution with the original defined interval. So let's get into this one here, and I think there's a couple that I will do and ask you guys to try and do a couple on your own just to see how you do with it. So find the definite integral. All right, so let's move on. We're still kind of looking at this as our normal u substitution. It helps if I turn my pen on. So in this case, again, looking at the denominator, if I look at if taking x plus cosine of x, if I take the derivative of that, I'll get the numerator. So u in this case will be x plus cosine of x. So if I take the derivative of that, we're going to wind up with 1 minus sine of x dx. So that one was pretty straightforward. Now what we're going to do is, again, we'll kind of ask ourselves, when x is equal to the lower bound and the upper bound, what is u going to be equal to? So here in this case, when x is equal to the lower bound of u, we're just taking that 0 and we're going to substitute it into, our u expression and say, okay, well, when x is 0, in this case, 0 plus cosine of 0 is 1, so 0 plus 1 gives a u value of 1. And we'll do the same thing with the upper bound. So when x is equal to pi over 2, what is u going to be equal to? So in this case, pi over 2, cosine of pi over 2 is 0, so pi over 2 plus 0 is just, and this is u is equal to pi over 2. And just like what we've seen with other examples where we did definite integration, we want to make sure, does the lower bound, the original lower bound value, actually produce another lower bound number? So if you notice, from 0 to 2, we went from a smaller number to a bigger number. So am I doing the same thing? Am I going from a smaller number to a bigger number? And in this case, I am. Pi over 2 is going to be bigger than 1. Okay, so we don't need to put a negative sign in front of our integral. So now it's time to go ahead and start doing our integration with our u substitution now. So in this case, I'm going to have my new definite integral will be from 1 to pi over 2. And I'm going to have 1 over u for the 1 over x plus cosine of x. And du is just the 1 minus sine of x dx, so du. Okay. And now we can see we can take the antiderivative of 1 over u, and that'll be the natural log of u in this case. And we're not going to add a constant here. We're evaluating it from 1 to pi over 2. So in this case, we're going to say natural log of the upper bound, pi over 2. And I guess we don't really need brackets there or absolute value stuff. We can probably just put parentheses because that'll give me a positive value. Minus the natural log of 1. And the natural log of 1 is 0. So natural log of pi over 2 is where we're going to wind up with for our accumulated value, whatever natural log of pi over 2 is. If you want to get your calculator and figure out what the exact answer is going to be, go for it, or the approximate answer is going to be, go for it. So moving on to example B here. Again, in this case, when I'm looking at this one, the only real candidate that I have for my u value is going to be the exponent of the e term. So u in this case looks like it's going to be 2 minus x. So if I take the derivative of that, that'll be a negative 1 dx, and the negative needs to be moved away, multiply both sides by a negative 1 again, and that'll give me negative du to be equal to dx. So now the dx expressions match, where I just had, 1 dx here and 1 dx here. So I do need to bring that negative in front of my integral when I work it out now. So let's go ahead and do that. So where am I at? We have a negative. Oh, no, I'm not there yet, because I forgot I'm doing definite integration, not indefinite integration. So again, when x is equal to 1 in this case, what's u going to be? So 2 minus 1 will give me a 1 here. And when x is equal to 3, what will u be? So 2 minus 3 will give me a negative 1. And here, my upper and lower bounds switched. Okay? So remember, if we go from the definite integral from a to b of some thing, f of x dx, if the upper and lower bounds switch, like f. So if we started off with here, let me just do this. If the upper and lower bounds are in the wrong order, so if the upper value is at the bottom of the integral and the smaller number is at the top of the integral, f of x dx, we have to change that to be negative a to b f of x dx. And that's what we're seeing here. So not only are we incorporating a negative sign from what we did here, but I'm also going to have a negative sign from the rules for switching the upper and lower bounds. So this is going to basically say negative times negative, giving us a positive integral. So we have a negative here, so that's negative, and then we have to have a negative from here, so that's negative again. So all of that just becomes positive, definite integral from -1 to +1, e to the u power du. So now we'll say e to the u power evaluated from -1 to 1 will give me e to the first power minus e to the -1 power. So that'll just be e minus 1 over e. And I don't know what that is as a decimal number. But there's your exact answer. So here, these are two more examples that I think that you will be capable of trying to figure out the solutions to. So go ahead and pause the video and try and work out example C and D and see what you get. When you're done, hit play and check your work with mine. Okay, and here you go. See how well you did. Hopefully we're getting these okay. On the example on the left, C, pay attention that the upper and lower bounds do switch when you evaluate u with x, or to find the value of u when we know the values of x are the upper and lower bounds. So we had a negative constant of 1/3, but then we had to switch it, so it becomes a double negative, making it a positive 1/3. And in this case, we wind up with 1/3 times e to the third power minus e. And on the one on the right, hopefully the u value didn't throw you off too much. I imagine if you tried taking u to be just the 2x, that's the exponent of the e value, if you try to take the derivative of that, you're going to just wind up with a 2, which doesn't really help you a lot to match anything up, or 2dx. So we have to look at u as being the entire denominator, 1 plus e to the 2x power, because when I take the derivative of e to the 2x power using the chain rule, I do get 2e to the 2x power dx, which that is what matches in the original integrand. So here, when I find u, I get 2 and 1 plus e to the 6th. When I check it with the upper and lower bounds of the original integral. And so with my u substitution, we wind up with a lower bound of 2, upper bound of 1 plus e to the 6th power, 1 over u du. And the antiderivative of that becomes natural log of u. And substituting gives us natural log of 1 plus e to the 6th power minus natural log of 2. So here, these are two more problems that I definitely think are in your wheelhouse that you're capable of doing. So go ahead and pause the video one more time and try working out these two examples on your own. And when you're done, hit play and check your work with mine. All right, and here are the next two worked out. The one on the left, we were able to simplify it a little bit to wind up with a 2 over natural log of 5. And the one on the right, we wound up with e minus 1 over e, or e to the negative 1 power. I'm not sure you'd ever see your answer left like that, but there you go. Hopefully you're doing okay with those. If you have any questions, of course, make sure you write them down and send them to me and get in touch with me. Let me know how you're doing. But now let's move on to the next examples. Here, these are both going to be relatively tricky because if it didn't tell you straight away by evaluate by completing the square, it's probably not going to be a very natural thing for you to want to think of because completing the square really isn't one of those things that gets emphasized a lot. You may have done it in Algebra 2 when you're working with solving quadratic equations, or if you're trying to convert a function from standard form to vertex form so you can graph it without a graphing calculator. But by it in and of itself, you really don't see it much outside of it. Now, we do see completing the square pop up from time to time with different integration techniques, and here is one of them. This won't be the only time that we see completing the square, but uh, let's maybe we need to get a quick refresher on how to complete the square just to make sure that you're okay with it and not having to spend a ton of time. Let me go look this up again because I forgot about it. Okay. Most of the work on both of these problems are really going to be algebra with actually completing the square. So let's go ahead and do this for the first one. I'm not going to do any calculus straight away. We're going to just take the expression that we have in the denominator, the x squared. Now, if you're following along with the notes I'm providing with this, you may just want to do this part on scratch paper somewhere because you probably don't have enough room to work everything out. But so plus 12x plus 37. Basically what we do is we take the a value, whatever this a value is, and we factor it out of the first two terms. Now in this case the a value is 1, so it's no big deal. It's just 1, and so factoring out 1 doesn't change anything. This will be x squared plus 12x. And what we do is we're going to add a new number here that I don't know what it is yet, and that 37, this 37 stays outside of the parentheses now. So that's a positive 37. Well, whatever this new number is, okay, this new number here, I'm also going to subtract it out here, okay? And actually, let me be real clear about this. In this case, we factored out a 1. Let me go ahead and just write that 1 here. We factored out a 1 here. I'm going to subtract the product of whatever value that I factored out and whatever that new number is that I'm going to put in that blank. Well, what is that number that goes in the blank? So in this case, we take the b value, the 12, and we divide it by 2, and we square it, which would be 6 squared, giving me a 36 here and a 36 here. Now the quadratic that you see inside of the parentheses, the x squared plus 12x plus 36, at this point, if we did everything right, that should be pretty quick to see, oh, hey, I can factor that one, and not only can I factor it, it's going to give me the same factor for both, or it's going to give me the same expression for both factors. So we're going to be, at this point, having x squared, nope, not x squared. Let me put it in factored form. X plus 6 squared, and on the outside of the parentheses to the right, the 37 minus 1 times 36 will give me a positive 1 in this case. Okay, so that is what we did to complete the square. So I can look at this as the indefinite integral of 1 over, and let me put it in this order so that way it might make a little bit more sense because this will tie back to what we saw in a previous example. 1 plus x plus 6 quantity squared dx. And this guy right here, again, what we're seeing here, this is the sum of two squares. Oops. So that is ideally something that's going to kick off the idea that we're going to do something with inverse tangent. Okay. So now let's give myself some space down here. And I guess I'll just rewrite the integral one more time here just so it's easy for everybody to see. 1 over 1 plus x plus 6 plus 6 quantity squared dx. And now what we're going to use is our rule for inverse tangent, where we're going to say 1 over a times inverse tangent of u over a plus a constant of integration. So we need to know the expressions for u and a. So in this case, going back to the beginning of the lesson, remember we're looking at this as du over a squared plus x squared. No, u squared. That's what it says. Let me just look at my notes to make sure. Yes, a squared plus u squared. So in this case, the u squared is the x plus 6 quantity squared. So that means u is just x plus 6. Oh, hold on. Okay, sorry about that. We had an announcement in the building. And if you needed to, if you wanted to, you could get du here to just be 1 dx. So du would just be 1 dx. But du isn't really used in the rule that we're using for the integration. We just need a and u. So I got u here. So now let's get a. So here, a squared would be the 1. So a would be a 1 again, because the square root of 1 is 1. So now we can just start plugging some things in here and see what we end up with. So I'm going to say 1 over a, which in this case is a 1, times inverse tan of u over a, which in this case u would be x plus 6 over 1 plus a constant of integration. Excuse me. So here, the 1 over 1 simplifies to be 1. Here, this will simplify. So my final expression would most likely be written as inverse tan of x plus 6 plus a constant of integration like that. And this one here, again, if you feel so inclined, by all means, go ahead and try pausing the video and identify the completing the square, because if you notice, most of the work on example A was really just the completing the square if you didn't remember how to do it. So let's go ahead and take a look at this one. And again, feel free to pause the video and try and complete the square yourself. We're only looking really at the radicand here. And I'm going to write it, where it's negative 9x squared minus 6x plus 4. So again, I factor out the leading term of, let's see, factor out the leading term from both the first two terms, and that will give me x squared plus 2/3 x. And then we're going to have some new number that we don't know what it is just yet. Or, I mean, you could probably do it in your head, but I just kind of work it out as we go. The plus 4 gets left outside of the parentheses, so I say plus 4 here. But then I have to say minus the same number that we factored out, minus a negative 9, times whatever that new number is going to be. And whatever that new number is, you divide the b number, in this case the 2/3. I'm going to take the 2/3, divide it by 2, and then square it. And then when I do that, 2/3 divided by 2 squared will give me 1/9. Now this one may not be quite as easy to see when you factor it, but when we factor the quadratic that we have now inside of the parentheses, I'm going to be left with negative 9 times x plus 1/3 quantity squared, and on the right side we're going to get a plus 5. Now the thing is that if we try to plug this in with the expression that we have now, this bit here, let me go to a different color here. This bit here is going to be very difficult to work with because essentially what we're looking at, if you go back and look at the very beginning of the problem, this is going to be uh, inverse sine or arc sine, okay, uh, based on what we're going to wind up with in the denominator. So this is going to wind up being 1 over the square root, and the square root is kind of a tip-off that we're using, either arcsine or arcsecant. And here we're going to say a squared minus u squared du. Well, what we want is we want something that's going to be relatively easy to work with for u squared here. And what I have right now with the 9 outside of the parentheses really doesn't work. Okay, so this is where what we want to try to do is we want to try and simplify that expression somewhat. And so this is how I'm going to do it. I want negative 9 times, and we're going to go ahead and just kind of expand that back out a little bit. We'll just say go back to the x squared plus 2/3 x plus 1/9. And if I distribute the 9 in, I'm going to get negative 9 x squared plus the 6x plus a 1. And that is factorable with a difference, and that's a negative right there. And if you want to, you can just kind of keep the negative sign out here and make this positive, make that positive, and make that negative. But when we factor this, that will be 3x, what was it, plus 1 squared. So this right here, specifically the stuff inside of the parentheses, that's what we're looking at as u. So like I said, most of the work that we're doing on this really is algebra, not so much not so much calculus stuff with the integration here, but you had to do a fair bit of work to complete the square on this one. So now we've completed the square. So let's go ahead and rewrite the integral with the information that we have now. So here I'm going to have the indefinite integral of 1 over the square root of, what did we have for the original, going back, we had a 5, there it is. So 5 minus the 3x plus 1 squared dx. Now we have some things to work with here. So the a or the u value in this case is going to be the stuff inside of the parentheses, just a 3x plus 1. We don't really need the derivative on this one because the rule, like I said, for sine, let's see, the rule that we have for this one is going to work out to be, where we're going to say the indefinite integral of 1 over square root of a squared minus u squared du for sine is inverse sine of u over a plus a constant of integration. That's the rule that we're kind of working with here. So we want to be able to identify the u value and the a value. So in this case, a squared is going to be a 5, or the 5 is going to be an a squared, so a itself is the square root of 5. And so now we can take those values and substitute it into the rule, and we're going to say this will be inverse sine of u, which is 3x plus 1, over a, radical 5 plus a constant of integration, and there we go with that one. So, nope, nope, nope. Dang it, dang it, dang it, dang it. I missed something here. I just looked at my notes and I missed something. So let me back up just a bit. Sorry about that. I got ahead of myself. I was like, yes, it's so easy, but I made a mistake here. And it was with this guy right here. Oh, didn't mean to do that. Did not mean to do that. So let's see. There we go. This is where I'm making my mistake at here. I do need to get du on this case here because what we're looking at, du in this case is going to be 3 dx. And if we look at the original function, 3dx and dx don't match. And that's where I was making my mistake here. I didn't go ahead and say, does this match this? And it doesn't. So I have to take out, multiply both sides by 1/3, and that'll be 1/3 du to be equal to dx. And now they match with my u substitution. So I need to put a 1/3 in front of my integral in this case. So basically we're going to have the same thing that we had a second ago, but it'll be 1/3 times inverse sine of 3x plus 1 over radical 5 plus the constant of integration. There we go. I'm trying to skip a step and it cost me, but at least we fixed it before we moved on. So the last two examples, and I know we're getting long on time, and I sincerely apologize. I don't mean to make these videos excessively long, but we have plenty of examples to work through. And these last two examples they're a bit of a challenge, and in fact, they're even telling you change of variables challenge. Okay, so this one isn't going to rely so much with anything that we were doing with transcendentals necessarily. It's more of just a kind of an extension of what we were doing with u substitution. So let's take a look at the example that we have on the left, example A. Again, we need to do u substitution to try and simplify the integral here. So I'm going to say, in this case, I'm going to make u to be the whole denominator of 1 plus the square root of 2x. Now, normally at this point, what we would do is we would just take the derivative of u, and I would say du is going to be something. But in this case, we want to change it up just a little bit. I'm actually going to take the 1 that's on the right side of the equal sign and move it to the left side. So I'm going to say u minus 1 will be equal to the square root of 2x. And that's going to be handy. And again, this isn't going to be something that's going to just jump out at you. This is something that'll take a little bit of practice to train your eye to identify. But that step right there is where things are, we're going to want to wind up coming back to that at some point. Well, now I want to take the derivative. So du, in this case, is still just going to, if I take the derivative of the left side, I'm still going to wind up with just du. And on the right side, when I do the chain rule, we're going to just wind up with 1 over the square root of 2x dx. And that right now doesn't quite match what we have, because if I'm just looking at the entire denominator as u, then I need to basically just get 1 dx left over. So I'm going to multiply both sides by the square root of 2x, and that'll give me the square root of 2x du to be equal to just 1 dx. And now we can see that if we go back and look, okay, well, so here I have 1 dx, and here I just have 1 dx, so now it matches. So that means this square root of the 2x, hold on a second, let me just double check something real quick before, because like I said, these are challenging. Let me just double check something real quick before I say too much. There we go. See, I was getting ahead of myself. That's where I was need them is calm down, slow down, and check. And it was the stuff I pointed out at the beginning that says, hey, make sure you watch for this. So here, this is the whole reason why we're doing this. Okay? So by taking that 1 from the right side and moving it to the left side, we wound up with the expression of square root of 2x was equal to u minus 1. And that's exactly what we have here. Okay? So I'm going to take that and I'm going to substitute it, and that'll give me, in this case, u minus 1 du to be equal to dx. So that is going to wind up getting substituted into the integral as opposed to putting a constant in front of the integral. So now that we have that, let's go ahead and try working it out and see what we come up with. So with my indefinite integral, we have, for dx, we have 1, or u minus 1 over u du. And that's how we're going to simplify this particular one. And if you prefer, you can say 1 over u times u minus 1 du to see how we're going to wind up kind of taking that. Actually, no, I wrote that wrong, because let's see, we can do this as a common denominator. I can write this as u over u, which would be 1, minus 1 over u du. And so now if I take the antiderivative of this expression, the antiderivative of the 1, in this case, is going to give me a u, because that's what we're doing our integration with respect to. And the antiderivative of the expression 1 minus the u will be a natural log of u plus a constant of integration. Well, in this case, we can substitute the expression that we have for u, which would be 1 plus the square root of 2x minus the natural log of, again, 1 plus the square root of 2x plus the constant of integration. And we'll see, whatever it is, the constant of integration is going to wind up, this 1 and this c, they're both going to just be constants, and they're going to add together. So that would just be a new constant. So I will write my final expression as square root of 2 times x minus the natural log of 1 plus the square root of 2x plus a new constant of integration when I combine it with the 1. And there's my solution that I'm going to have here. And the last one, this is one that I feel that you could probably do without really any assistance from me. That's just a straight definite integration. It's not, I don't really think of it so much of as a challenge for this one. I'm not really sure that that's really a challenge, because we could have seen that on just our u substitution when we introduced that for definite integration. So let's go ahead and see what we wind up with here. Guess let me get a new color. So here I'm going to look at u to be the denominator, 3x plus 1. And so if I take the derivative of that, du, I'm going to get 3 dx. And the 3 dx doesn't quite match what we have here. And it's definitely not going to match with this 5, but this 5 can be pulled out as a constant. So this is really like saying 5 times the definite integral of 0 to 4 of 1 over 3x plus 1 dx. So the 3 dx doesn't match the 1 dx that we have in the integral itself, or the integrand of the original problem. So multiply by 1/3, and that'll give me 1/3 du to be equal to 1 dx And so now we have that match, 1 dx here and 1 dx here, but I do have to take that 1/3 as a constant and multiply it with that 5. So when I do, we're going to end up with 5/3. And I guess I need to get my x and my new upper and lower bound here before I go too far. So let's say when x is equal to 0, u is equal to 1, and when x is equal to 3, u in this case will equal a 8, a 4. Yeah, 4. I don't know where I'm getting a 3 from. That would be a 13. There we go. Oh, golly. Just clean it up. 4u will equal to 13. There we go. All right, so back to the green here. And so now I have my new interval from 1 to 13. And in this case, we're going to have 1 over u du. So we get 5/3 times the natural log of u, evaluated from 1 to 13. So 5/3 times the natural log of 13 minus the natural log of 1. And natural log of 1 is 0. So that would be 5/3 times the natural log of 13. There we go. So like I said, this last example isn't so much anything to do with transcendental integration with U substitution, but it's definitely related, I guess, because we're still talking about U substitution even with the transcendentals, and we've been practicing definite integration for sure. But that's going to wrap it up for this video, guys. Thanks for watching. I hope you learned something, and we'll see you next time. Take care.